Our next set of identities, formulas, call them what you will, concerns double angles. Now, it's important to think of these formulas as double angles, not just 2 theta, because it's not restricted to just theta and 2 theta, it's double the angles. So I'm going to create them by looking at the 2 thetas, because obviously 2 theta being double theta. I could rewrite sine of 2 theta as the sine of theta plus theta. And then, using what we saw yesterday, sine, cos, sine, if it's the sine, that's the sine. I end up with sine theta, cos theta plus cos theta, sine theta. They are, of course, the same thing. And so there's our first one. Sine of 2 theta is 2 sine theta cos theta. It also means that the sine of 4 theta would be 2 sine 2 theta cos 2 theta. It would mean that the sine of 10 theta would be 2 sine 5 theta cos 5 theta. It's double the angle. So that's when we use them, we double the angles. So sine 2 theta. All right, let's create cos 2 theta. So again, I'll rewrite it as theta plus theta. Cos, sine, sine. If it's not the sine, it's not the sine. And we get cos squared minus sine squared. Now the interesting thing with cos 2 theta is because of the other trig identities we know, I could express this in a different way. So sometimes it's useful, cos squared minus sine squared, but sometimes we might just want it in terms of cos. So I could change the sine squared to be 1 minus cos squared, and we get 2 cos squared theta minus 1. But there's another way I could write it. If I wanted it in terms of sine squared, then for the cos squared I could substitute in 1 minus sine squared, and we get 1 minus 2 sine squared theta. Now, how do I remember those? Well, because the first one you'll notice is cos squared minus sine squared, I remember that the positive is with the cos squared, the negative is with the sine squared. So when it comes to the other two, they're very similar, but cos squared's positive, so it must go 2 cos squared minus 1, whereas in the second one, sine squared's the negative, so it goes 1 minus the 2 sine squared. So that's how I try and keep it clear in my head so I don't muck it up. These last two will become very useful later on, and later on I will remind you that I told you that these two will be very useful, and you'll go, when did you tell us that? I don't remember that. But I'll explain it a little bit later. Tan 2 theta, let's create our tan 2 theta one. So tan plus tan on 1 minus tan tan. And so we get 2 tan theta on 1 minus tan squared theta. So to summarise, our double angles, sine 2 theta, 2 sine theta cos theta. Cos 2 theta can be cos squared minus sine squared. It can be 2 cos squared minus 1. Now, where I said it's useful is because sometimes we rearrange it like this and make cos squared the subject. And cos squared becomes a half of 1 plus cos 2 theta. And later on when we're looking at integration, and we want to integrate cos squared theta, it's a lot easier to integrate the cos 2 theta than the cos squared, so it allows us to do a substitution. That's where this one will become very handy later on. It could also be 1 minus 2 sine squared theta. If I made sine squared the subject of that, we get a half of 1 minus cos 2 theta. So again, very similar, but remember, sine squared associate with the negative, so we get a half of 1 minus cos 2 theta. The cos squared originally was positive, so we get 1 plus cos 2 theta. And tan, 2 tan theta on 1 minus tan squared theta. All right, let's play. If cos theta is 2/3, we're going to go and find tan 2 theta. Well, in order to do tan 2 theta, I'm going to need to know the tan theta result. So I'll draw myself up a little triangle. The other side's root 5. Of course, I'm assuming here that theta is actually acute. They haven't told me, but I guess if they don't tell me, I'm going to assume that. So we get tan 2 theta, 2 tan theta on 1 minus tan squared. Let's substitute in. And a bit of tidying up to do there. Fractions on fractions, but eventually, there it is. All tie these up to be minus 4 root 5. Now, that's interesting. Because if I did just assume theta was acute, and I've ended up with tan 2 theta being negative, what can you actually tell me about that original acute angle? Bingo. Got to be more than 45. Why? That's it. When we double it, it must have ended up with an obtuse angle to make tan negative. So we must have had an acute angle originally bigger than 45. So when we double it, it's going to be bigger than 90. Find the exact value of sine 5 pi on 12 cos 5 pi on 12. Now, there is a temptation here to look at 5 pi on 12, which is, look, I've got to be honest with you, I still convert these into degrees to think about them. 5 pi on 12, would that be? Was it 75? So you could use our formulas from yesterday to go, oh, how can I get 75? That'll be 45 plus 30, and do that. But if you notice the pattern, sine cos, well, we've got something very similar to that. Sine 2 theta is 2 sine cos. So actually, I could say, well, hang on, I've got sine 5 pi on 12 cos 5 pi on 12. Well, that would just be a half of 2 sine cos. And now I can use the double angle. Double 5 pi on 12, so sine of double 5 pi on 12, but that turns into an exact one, 5 pi on 6. 5 pi on 6, so the acute angle is 30 degrees. We're in the second quadrant, aren't we, 5 pi on 6? Sine's positive. Sine of 30 is a half, so half times a half, we get a quarter. Certainly a lot quicker than trying to work out what sine 5 pi on 12 and cos 5 pi on 12 are, and then multiplying those two together. Okay, I'm now told cos is 2/3. Find the exact value of the sine, half a theta. But it's okay, remember we're dealing with double angles. Theta is double half theta. So I could say, use the sine squared one. Now, notice I've written it with the double angles. So sine squared theta is a half of 1 minus cos 2 theta. Well, if I replace that, remember it's just one's double the other, I could come up with this little formula. Sine squared, well, we want to find sine. So sine squared theta on 2 is a half of 1 minus cos theta. I've still got that angle is double the angle on the left. Now, they told me cos theta is 2/3. So I can substitute in, and I now know what sine squared is. So therefore, sine is plus or minus. Again, without more information, I can't really tell whether that one's going to be plus or minus. Let's prove this identity. Now, what do I see when I look at this one? I see the double angle. Certainly I see that. We've got to prove it's tan x. 2x is double x. But I suppose actually the first thing that jumps in my head is tan is sine on cos. And I've got a fraction on the left-hand side. So I'd like to end up with sine on cos, which now is leading me towards which one of the cos 2x to use. I think on the top of the fraction it would make sense to use the sine one. So I'll replace cos 2x with 1 minus 2 sine squared. But on the bottom of the fraction it would make sense to use the one in terms of cos. So I hopefully will end up with sine on cos. So what do we get when we tidy all that up? The 1 minus 1's cancel. 2 goes in the top and bottom. Sine squared on cos squared is tan squared. And of course the square root of tan squared. And we've got our answer, tan. So we don't necessarily have to use the same result for cos 2x each time. We're just picking ones that are convenient to help solve the problem. Here's a nice HSC question. I always like showing this one because you can waste a lot of time on this question. So look what you have to prove. And what a lot of people did in that particular HSC is they saw sine 3 theta and cos 3 theta and said, okay, well, I know how to come up with a result. I could rewrite 3 theta as 2 theta plus theta and then go and do that. But algebraic fraction, what's our rule? Golden rule. Factorise first. Well, it's already factorised. But then we get ourselves a common denominator. And look what happens to the numerator. We get sine cos, cos sine. Hang on a sec. That looks familiar. And so actually on the top, what we've got is the sine of 3 theta minus theta, which is just sine 2 theta. And we've got sine 2 theta, and on the bottom, by the way, you might have missed my subtle thing there. See, I also took advantage and multiplied top and bottom by 2. So I ended up with, on the bottom, 2 sine theta cos theta, which is sine 2 theta. My sine 2 thetas cancel, and I get 2. Now, it still works the other way, but by geez, it was a lot longer because they had to work out the result for sine 3 theta, work out the result for cos 3 theta, and there was a lot more algebra involved in solving it. Yeah. Okay, let's have a look at another one. Wow, 1994. Geez, we really are going back now. So 2 tan A on 1 plus tan squared, and we've got to end up with sine 2A. Oh, hang on, almost made a silly mistake then. Of course, I'm looking at the left-hand side and I'm thinking, hang on, isn't that tan 2A? But it's not, because what's different? Yeah. If it was tan 2A, the bottom would be 1 minus tan squared, not 1 plus tan squared. So, okay, I want to prove sine 2A. I think I'm just going to change all my tans into sines and coses and see what happens. So I hope that's what I did anyway. Yes, that is what I did. Fraction on fraction, I'm going to multiply everything by cos squared. If I multiply everything by cos squared, there we go. Quite nice. Bottom of the fraction is 1. Top of the fraction, there's 2 sine A cos A, which we know is sine 2A. So I've got sine 2A on 1, which is sine 2A. All right. So that's the first section we'll look at today.